Hello everyone, this is Srilekha Mitai. Today I will be speaking about heterogeneous multi-type package design. This is presentation for EEE 236 class. The topics which we're gonna discuss in this presentation is about IC packaging and basics. The second one is different packaging techniques, where we discuss about monolithic versus heterogeneous, and the third one is different heterogeneous option, and the fourth one is EMIB, that is embedded multi-die interconnect bridge package, and also we compare EMIB with other options and then we can conclude it. In this slide, let's discuss about integrated circuit packaging. All the integrated circuits enclosed in a case in order to prevent from physical corrosion damage. This process is called packaging. This is the last step in device fabrication. The package is further taken for the post-silicon testing. The process or the steps of packaging must be followed very carefully for better power and performance of the chip and also for the cost-effective solution. In this slide, let's discuss about the package design consideration. The three important things which we have to consider about packaging are electrical, mechanical, thermal, and economical. So let's talk about electrical. The electrical characteristics of signal routes are different for on-chip and off-chip. So off-chip route material should offer lower resistance and capacitance elements for providing better signal transmission. Coming to the mechanical thermal, the design should be saved from potential damages and also it should offer effective heat dissipation from chip. We can also consider the materials like thermostat, thermoplastic or ceramic, which have the preferred characteristics. Coming to the third one, that is economical. Careful attention should be paid in choosing the appropriate packaging to make it viable for the production, considering complexity, heat, dissipation of the chip or the process technology. Here, let's look into the different packaging techniques. The packaging techniques are classified into two, based on assembly of the submodules or the designs on the die. Let's look into the definition of monolithic or homogeneous. Several components of a system design are manufactured on a single die here, whereas coming to the heterogeneous, this technique allows discrete components of the system to be on the same package. Let's talk about traditional monolithic package design. Here, different IPs packaged on same die. As the name indicates, mono means single, lithos means stone. So the package design uses single IC package for the entire system. In figure, we can clearly see how the CPU, IO memory, GPU and other IPs are all manufactured on a single package. Let's look into the advantages and disadvantages of monolithic circuit packaging. Coming to advantages, it is more denser and there are no external interconnect parasitic like resistance and capacitance effect to it. And there is no additional cost of making interconnections. Coming to disadvantages, it has poor isolation between the components and there is no flexibility to mix and match IPs from different process nodes. And the third one is system on chip and production might have to be delayed in certain cases till all the IDs are showing the better yield, especially on smaller technology nodes, like example 10 nanometer one. The slide explains about the heterogeneous design and we can also clearly see in the picture the different IPs can be packaged onto a same system. Suppose if we consider die 1, die 2 are of different IPs, they can be packaged onto a same system. Not only that, each IP can independently packaged on a different process nodes. This is useful for capturing the market. And also we can see how Intel recently made a deal with AMD and integrated their GPU using heterogeneous technology to compete in the market. And we can also see that how the Moore's law is motivation is here, because as the days goes, it is becoming very costly and difficult to scale and produce dies without yield issues. Let's talk about different heterogeneous packaging. So coming to the different packaging types in heterogeneous, the first one is multi-die package, the second one is silicon interposer, and the third one is embedded multi-die interconnect bridge. Coming to multi-die package, in this method, the dies are connected through the substrate package as shown in the figure. We can see here how the die 1 and die 2 are connected with the package substrate. Coming to the advantages and disadvantages, it has a poor density of die package connections and also die to die interconnects. Talking about silicon interposer, we can see in the picture how die 1 and die 2 are connected with the silicon interposer. In this method, the inter-die communications happen through the silicon interposer. So, all connections on dies have to be made through the interposer. So, if it is connecting to the die 1, die 2, die 3, everything should be connected with the interposer. So, it is very expensive due to its large size and through silicon vias. This offers more connection density compared to multi-die packaging. Coming to the advantages, it has good density of die interposer connection and die-to-die interconnect. And the disadvantage is its higher cost of larger interposer and through silicon vias. Talking about EMIB, in this method, small silicon bridges are embedded into which leads to a tighter interconnect density on the periphery of the die as shown below. So we can see in the figure how die 1 and die 2 are connected with the silicon bridge. So once we compare the silicon interposer image and the EMIB image, we can understand that how the silicon bridge differs in the size. Whereas here the silicon bridge is very small. So we can understand this is very cost effective. And coming to the advantages, has good density of die bridge connections and die to die interconnects. And it doesn't have silicon vias unlike silicon interposer. So we can say it's a cost effective than the silicon interposer. Looking into 3D SiP technology for next generation platforms, this uses embedded multiple interconnect bridge. So here in the picture we can see how the XCVR, that is trans receiver, DRAM are connected with the EMIB. The figure shown here is Interstratix IO chip FPGA, which has discrete modules packaged onto a single chip using EMIB heterogeneous package technology. Let's compare the EMIB with the silicon interposer. So looking into the figure 1 and figure 2 and we compare, coming to the figure 1, we can clearly see how the small silicon chip embedded inside the substrate. And also the EMIB dimensions doesn't limit the number of dies that can be integrated. So we can see the FPGA die is connected to the dies on either side with a small silicon substrate. Coming to the figure 2, that is silicon interposer, we can see how the silicon interposer on substrate that extends the entire die. So it also requires more microbumps and it has scalability limits as it has to spread entire die. It is very expensive technique. MIP allows the die IO bumps to be placed as close as possible to the edge of the die. We can clearly see in the image in the previous slide, which I have shown, there is a short interconnect wires and the short interconnect wires improve performance due to the lower loads. Coming to the interposer, it uses a large interposer that spreads out the entire die. So large number of IO or bumps are deployed to make connectivity, which in turn results in a longer interconnect and loading. This finally results in the low performance. Talking about connectivity in EMIB, it is a two-step connectivity process. We can see in the image how it is connected from bump to the package traces. Bump are the balls which we can see in the image at the bottom. Connected to the package traces are the thin lines, and the package traces are connected to the ball which is below the die. So, due to which it has reduced manufacturing complexity and superior signal and power integrity. And because of this, power supply rejection ratio, crosstalk, ICR will be lower here. Looking into the silicon interposer connectivity, it is a four-step process. It has to connect from bump through TSV, TSV to bump, bump to package trace, and package trace to package ball. So because of this, it has manufacturing complexity. Not only that, it has yield loss, poor signal integrity, and IR drop too. Continuing to talk about silicon interposer, TSVs also add series of gaps and resistance causing high-speed design challenging. Crosstalks in the interposer routing and coupling between TSVs impact ICR. Signals to power rail coupling through TSVs impact power supply rejection ratio too. In the end, it's always the monolithic package design which we need for better performance and utilization, and also for less congestion. Studies clearly show that there is a performance degradation of about 1.5 nanoseconds using interposer packaging techniques, which might be better if we use EMIB. However, the next gen platforms need heterogeneous for faster time to market and economic viability. Thank you.